boundary of omega. So we require that U is a solution of this equation. And of course, this solution depends on the geometry of the problem, because it depends on in which way we have fixed A inside omega. Then we want to minimize the cost functional. So we consider the following optimal control problem. We want to minimize this cost functional with the condition that you satisfy the equation 1. And for the sake of simplicity, I take this very simple form for the cost functional in such a way that we can rephrase this optimal control problem in we can obtain the minimizer of these optimal control problems, minimizing just one single integral functional. And indeed, under these assumptions, you have that if U is a solution of the state equation, if you multiply this equation for U, you have that on the left-hand side, integrating by part, you have that the energy of the gradient to the square is equal, multiplied by sigma, is exactly equal to the opposite of the cost functional. So under this assumption, this the previous control problem can be rephrased minimizing just a unique functional that is the following. In the first term of the functional, you have the integral of the gradient of U to the square multiplied by sigma. And the second term is the cost functional. And so unfortunately, in the problem is that this in the way we have formulated this problem, the problem is ill-posed. Indeed, it happens that in general, there are no solution to this problem. And this was proved by Murat et Tartar and Kohn-Strang in 1985 and 1986. And indeed, they proved that optimal configuration minimizer cost functional, GU, does exist for general cost functions. So there is a problem of existence, and to overcome this problem, the Murat Tartar and Kohn-Strang suggest to introduce a perimeter penalization. That is, we add in the cost functional the perimeter of the set A, which means the measure of the interface between A and its complement. I will be more precise about what is the perimeter of a set in the sequel. For the moment, you can think that this is the n-1 dimensional Hausdorff measure of the boundary. Then, if we add this penalization, we can prove the existence of minimizers. And this is also a natural condition to add this perimeter penalization from the physical point of view, because you are also taking care of the surface tension. And the adding of this perimeter penalization avoids that A can disintegrate in infinitesimal part spreading inside omega. So this term, as we will see, has also a regularizing effect. Also, in the following, would be important to handle with constrained block problems, in the sense that the measure of the set A that we have inside omega could be fixed. Okay, I want to present some also related some related functionals introduced by Muratov and Novaga very recently, that is very related to the previous functional, but there are some difference. The functionals is almost the same. And but the difference here is that there is the container. There is no container, in the sense that now the container is the ORN, and now A will denote the droplet, the charged droplet. So now the function sigma is equal to beta inside A, where beta is the conductivity of the droplet, and one outside, and one is the conductivity of the vacuum. And so this is the reference, no container at all. The ORN is the container. And now the state equation is also a little different, in the sense that here rho is the charge density, but the important thing is that here rho is not fixed. So rho, it can change, is another unknown of the problem. So we have more, there are more free unknown. And it is normalized because here in the functional, the total charge is put here in front of the integral, is in evidence here in front of the integral. So you have the condition that the source, source charge here have integral 1 on the ORN. But the functional is almost the same. Indeed, you have the integral of the gradient to the square, and the integral of the square of the density change, plus a perimeter term. Okay, and under Muratov and Novaga introduced this functional to modelize the change droplets, and they proved that for small capital Q, the shape of the charge droplet is spherical. Okay, but let's go back to the problem of the two materials. So I will think about that in the future. So this is the functional. Here I want to split in the following the functional into two terms. That is the terms which is the term with the bulk energy. That is the integral term. And the other term is the interfacial energy, that is the perimeter term. I want to split two terms because there is an interaction between these two terms to prove regularity, as we will see in the following. So I will call this integral part the bulk energy, and interfacial energy the perimeter. Okay, and it's important to understand the relation between these two parts of the functional. And the first result I want, regularity result I want to mention about the functional I introduced in the first slide is the following, proved by Ambrosio Buttazzo in 1993. So the functional is the same. You have the interface energy in red, that is the perimeter, and you have a bulk energy that is the gradient to the square with the two different regime. In A, you have a constant alpha, in the complement you have constant beta, and here you have the source term, which can depend on the x, and also from the function u. And u is a Sobolev function which have a zero datum on the boundary. A is an admissible function, which means that A must have a finite perimeter. So the term in red, of course, must be finite. And Ambrosio and Buttazzo proved that for this functional, the solution, the minimizers of this functional are C1 alpha. C1 alpha are the Elder continuous. Minimizers are Elder continuous, and the set A is relatively open in omega. So this is not, this information is topological information, not regularity information for the set A, but is on the road to prove the regularity of the set. So they are able to say that the set A is relatively open inside omega. But in the same year, Fanwali proved also the regularity of the interface for the same functional, but without source term, that in any case is a lower order term. And indeed, Fanwali proved in 1993 that the minimizer of this functional, that is almost the same as above, with these two different, as I told you here, there is no source term, but now on the boundary of omega, to avoid triviality, you don't have zero, but have some prescription for u. U is equal to u0 on the boundary of omega, and also you can have some restriction on the set A on the boundary of omega. And under this condition, Fanwali proved the following regularity result. That is, minimizers of this functional are either continuous, but precisely the exponent of Elder continuity for the function u is 1/2. And this 1/2 is an important threshold, as we will see in a moment. And moreover, the interface of the set, so the boundary of the set A, is a C1 alpha hypersurface away from a singular set. So the boundary of A can be singular in some points, but the measure of this point is 0. The Hausdorff n-1 dimensional Hausdorff measure of this set must be 0. And the singular set is closed. And this regularity result is a result we will see also in the future, because is a good regularity result. Okay, so I want to precise some, as I told before, something about what is the perimeter, what are the sets of finite perimeter. And I want to recall that a set is a finite A is a finite perimeter if is the distributional function of the gradient of the characteristic function of A. So if you do the gradient of the characteristic function of A and call this gradient in the distributional sense mu A, this must be a random measure. And this random measure must satisfy the divergence theorem. So if you integrate over the divergence of some field T, this is equal to the integral over Rn of the scalar product of T for the measure mu A. And more important for our consideration is the perimeter of the set A inside any F in Rn is equal to the total variation of this measure. But more useful, it is also equal, the perimeter, to the n-1 dimensional Hausdorff measure of the reduced boundary of the set A. And what is the reduced boundary? The reduced boundary is the sets of points where there exist the Bezikovich derivatives of the Bezikovich derivative of the measure mu A. It is a vector with norm 1. But this is a rather technical condition, so is maybe very interesting for us is the following Federer's theorem that states that if A is a set of finite perimeter, then the reduced boundary of the set A is contained in the essential boundary. And what is the essential boundary? This is very easy because the essential boundary is the complement of the set of points that has zero density or density 1 with respect to the Lebesgue measure. So here A0 and A1 denotes the points with zero density of A and density 1. The complement of this set, of course, the union of A0 and A1 is what is A1 is essentially A, and A0 is the complement of A with respect to the Lebesgue measure. So the complement of this set is the boundary, the essential boundary. So A1 is, in some sense, are the points that are in the inner of A with respect to the Lebesgue measure. And while A0 is the point, is sets of points that are in the complement.
Excuse me?
Yeah.
Yeah. I have a question. This set, the boundary of A can intersect the boundary of omega?
The boundary of A can intersect the boundary omega, but you are not evaluating the measure of the intersection.
Okay.
Because omega is open.
Okay.
And so this give no contribution.
Okay. So all this would be, means when you say boundary of A in omega, so only that part of boundary which is inside omega, right?
Yes,
not
yes,
the one
correct.
It's okay, fine. Thank you.
Thanks. Okay. And let's also draw a picture to comment about this definition. So here in red, you can see the set. Okay, I call this E instead of A, but of course it's the same. So you have the set here, E in red, And what is the essential boundary? The essential boundary is the one in red. So these green parts are not in the essential boundary, because these green parts, for example, isolated points and points with zero density with respect to E, are not in the essential boundary. And because they have zero density. And further theorems tell us that the difference in measure between essential boundary and reduced boundary is zero. The regularity, one regularity question that we will ask in the following is what happened to the difference between the topological boundary and the reduced boundary. If we don't have any condition, the topological boundary of set E could be also the whole omega. So it would be possible that the boundary of the set the set is dense inside omega. So in general, this is not true that this is zero. But so this is first information about regularity is that this is zero, as we will see in the future. Okay. And so an observation about the interaction between bulk energy and interface energy, and why the threshold 1/2 is critical for further regularity. So if you assume that U is elder continuous with an exponent that is greater than 1/2, so here you have 1/2 plus positive eta. Then you can you know that the gradient to the square decay when you integrate it over a ball of radius r, decay faster than the power of r to the power n minus 1 plus something. And so in this case, you know that this energy decays faster than the perimeter, because the perimeter inside a ball of radius r decay exactly as r to the power n minus 1. So in this case, if you have this regularity assumption for you, you have that the boundary of A is almost area minimizing. That is, the perimeter of the set A inside BR is less or equal to 1 plus r to the power 2 eta for the perimeter of any other competitor F. And of course, the competitor must coincide with A outside of the ball. So you have to know that the symmetric difference between A and F must have a compact support inside BR. And Tamanini proved in 1982 that almost area minimizing are indeed very regular in the set. They share the same regularity of minimal surfaces. And so for almost area minimizing, you have that the reduced boundary is C1 alpha, and also the measure or the difference between the topological boundary and the reduced boundary inside omega is 0 for every S greater than n minus 8. So up to dimension 8, you have no singularity at all. And so this is the best regularity you can have for interface. But of course, you have this only if you can assure that the bulk term decay in a good manner. So if you know that U is in C1 half plus something. And here is a list of persons that give some contribution to the proof of the regularity. The regularity I mentioned here is called the full regularity. Of course, in general, you can't expect full regularity. But under some condition you can prove it. And here there is a list of people that work on this subject. Benita Carrozza, Irene Fonseca, and Passarelli proved a result that we will see in the following, 2014. And also De Filippi e Fingalli proved a result in 2015, which is related to another result that also we will see in the following. Another result proved by Fusco and Yulin in 2015. And there is also a result of myself and Nicola Fusco in 2011 and Fanwalin and Kohn in 1999. Okay, I want to also mention some results about how you can handle the constrained problem. I will go very quickly in this part because it's a technical observation. You can handle with constrained problem thanks to the following results. So if you have the usual functional that I now write in just in one row. So I assembled again the bulk part and interface part. So here calligraphic G denote the both term, bulk term and interface term. If you minimize this functional under the assumption that the measure of A is fixed, then you have some problem because you can't manage you can't take any competitors to prove the regularity, and this is a problem. But these results come in help because in 2011 we proved that indeed if you penalized the difference between the measure of set F and D here in red, then you can prove. So okay, if you consider this functional adding the penalization of the difference between the measure of F and D, you can prove that minimize F of the constrained problem. If you take lambda sufficiently great, so lambda greater than sufficient big, so lambda greater than lambda 0, then UA is also a minimizer of this penalized functional. And this is an unconstrained functional. So for this functional, you can perform all the variations you like. So you can take all the competitors you like. You are not constrained to preserve the measure of the competitor. And also I want to quickly mention that when alpha and beta are close together, in the same paper we are able to prove that indeed the U is either continuous with exponent greater than 1 alpha, and is, as I told you, can allow to prove the best regularity for the interface you can prove. And indeed, the singularity, the measure of the singular part is 0 for all s greater than n-8. And now become the new part. So the no, sorry. Also, I want to mention what happened here without any restriction. So if alpha and beta are not close together but are far apart, because in 2015, Fusco and Yulin proved the results also in the case that alpha and beta are far apart. And indeed, they proved a reduction of singularity. Indeed, they proved that the measured singular part is 0 for an exponent that is better than n-1, but is n-1 minus epsilon. So they proved that if UA is a minimizer of the constrained problem, then there exists a subset of the boundary, that is relatively open inside the boundary, and this is a C1 sigma hypersurface. And the complement of this capital gamma, that is the singular part, has a measure 0 with respect to the Hausdorff measure n-1 minus epsilon dimensional Hausdorff measure. And this is called the reduction of singularities, because you have much information thanks to the presence of this epsilon here. And this result was proved independently in the same year, but using a totally different technique by De Filippis and Figalli. And now I want to come to the new part. There are few results under these assumptions. If we think about functional, in which the gradient, the growth of the gradient is not to the square, but is p groups. We have p groups condition on the gradient. So the model case, in this case, the model case is the integral of the square. No, sorry, not the square. The p. We have the p power of the gradient. So this is almost the same. The only difference for the model case is that you have a p here. You can also think of some generalization of this because you can take general capital F and capital G that gives you. These are two function density function that are different inside A and inside the complement of A, and indeed you can consider the constrained problem again, minimizers of this functional, and for the minimizer of this functional. There are few results. Very few things are known. Indeed, the only results that I know are the following. So these are the assumptions on the density capital F and capital G, but I go quick here because these are technical condition. Here you have in G1 the growth condition, in G2 for F for G, and C1 and C2 are convexity condition for capital F and capital G. These are very, very common. This is the quasi-convex condition, and here is the growth. But you can think about the model case. In the following, you can think about this model case where you here have the gradient to the power p. And the only result that I know is this. A partial regularity results by Menita Carrozza, Irene Fonseca, and Antonio Passarelli di Napoli in 2014. They proved that minimizers of the constrained problem they prove also other things, but among other things, they prove the following. About the interface, they prove the following. They prove the partial regularity. Partial regularity is in another spirit. Which is, what does it mean, partial? Means that you don't prove the regularity in the whole omega, but you take an open set inside omega, but with the same measure. To be precise, the measure of the difference, the Lebesgue measure of the difference between omega and omega 0 is 0. And inside this set omega 0, you prove the regularity. So you prove the best you can have. You prove the Elder continuity with any exponent between 0 and 1, and you prove that the reduced boundary, the interface, is regular up dimension 8, so have the same regularity as like minimal surfaces. But you only prove this, so this is the reason why this is only partial regularity, because you prove this regularity inside omega 0. That is another open set that is inside omega, that have the same Lebesgue measure, but of course, a priori, you can think that all the singularity of the original interface could be in the complement of omega 0. So this gives no information at all for the singularity in the whole omega. But in any case, is results, partial regularity results tell us that inside omega 0 you have all the regularity. And it is interesting to observe that omega 0 is obtained considering exactly the set of points when the bulk energy decay in a good manner. Because here, as you can see, you have that the integral or the gradient to the power p faster than rho to the powers and n-1. Okay, and so there are some questions are open. This first question is what I am able to prove. That is this is a topological information. That is the Hausdorff measure, n-1 Hausdorff measure of the difference between the topological boundary or between the topological boundary and reduced boundary, or if you like, the difference between the topological boundary and the essential boundary, which is the same for thanks to the Federer's theorem, is 0. There are no points in the topological boundary. There are no points that have density 0 with respect to the set A. There are almost no points, almost with respect to n-1 Hausdorff measure. And this is the first question. But the second question is very interesting, but there is not an answer for the moment. So if you call regular A the sets of points where the topological boundary is C1 alpha in a neighborhood of the point X, and singular, you have the complement of this set. This is the singular part S of A. Can you say that the singular part has a measure 0, Hausdorff measure 0? And this is an open question. So there is not an answer to this question. And again, okay, this is the picture as before. And so we can answer to this question. The measure between topological boundary and the root set boundary is 0. Okay. And you can prove this because I am able to prove that the solution of the constrained problem, for the solution of the constrained problem, the density, and so you can see what the reason of the title, you have a density lower bound for the perimeter. Indeed, if you take an open set inside omega, there exists a constant depending of u, and depending on the gradient, the norm of the gradient of u in LP, such that for every x naught in that is on the topological boundary, and for every ball centered in this point that is contained in U, you have that the perimeter of A inside this ball is not too small, is greater than a constant related to the r to the power n-1. So to the measure of the ball n minus 1 dimensional ball over radius r. And moreover, you know that the difference in measure between topological boundary and the reduced boundary is 0. And very quickly, in which way we can prove these results? To prove these results, you have to consider this comparison function. So you take a ball inside the omega and consider the function v, which minimizes the integral part, the bulk part of the functional, and which have the value on the boundary of the ball prescribed by the original minimizer u of the constrained problem. So you take a ball and minimize the energy of the bulk part with the prescribed value on the boundary, and the value is exactly the value of the function u. So you take this competitor. Here you can think the capital F is the gradient of omega to the power p. And if you take this comparison function here, you can prove these things. You can prove that the comparison function is indeed, you can prove higher integrability for the function u and also for the competitor. And this is important to have this higher integrability. This is very important to prove that the function u share the same regularity as the competitor, and the competitor is minimizers of the P Laplacian, so is regular. And so you have these two functions, the function u, the minimizers of the original problem. You have the competitor, you have higher integrability of both. Then we can end the comparison. And the comparison tell you that the following lemma is true. And the following lemma tell you that if you are in a point where the measure is almost all the measure of the ball, or is almost zero, so you have two cases. You take a point when you take a point with small density or density that is almost one. You have to have these two conditions, that the intersection between A and the ball BR is small, related to the measure of the ball, or you take a point where the measure between the difference of the ball and the set A is small. Under this condition, so if you are in a point that have small density or big density, then you can prove that around that point the gradient decay in a good manner, because decay better than the decay has the radius to the power n. And this is proved using the comparison technique. And here you very quickly I can show you in a precise way how can you prove the comparison. Because here you have that denote with V the comparison function and U the minimizer of the constrained problem, and you write down the equation that they satisfy. So the question for the comparison function is this: you have the divergence of f, capital F, the divergence of capital F of gradient V equals 0, and here you have the Euler equation for the U. And for the U, you have two different zones, as you can remember, because you have in set E where you have some conductivities, and so here you have some constant, some function G, and in the other set you have another one. But then you can take the difference between these two equations. So you take the difference, and there is a common term that go away. So on the left-hand side, we use the ellipticity, and on the right-hand side, we use the growth. Okay, you use this condition. In the case, easy case, when P is greater than 2, you prove using the convexity condition, you prove that you can look at this one. The integral on the ball of radius R alpha between the difference of the gradient of V and the gradient of U to the power P is less or equal to the integral. Here the integral is, and you can see, intersection with A, because of in the complements you have a term that is raised in the beginning. It was raised here and in the beginning when we performed the difference. Okay, so you have now used the higher integrability, use the higher integrability, use the equation. Here in question 2, you have here in front of this the something that is small by hypothesis of the lemma, because I recall you that we have this assumption E and E. So these are small. And so you can perform here the calculation and prove this is small. And so you inherit the same regularity of V. V is a minimizer of P Laplacian, and so you decay in a good manner. There are some technicalities, but you can if you want, you look at the proof and what tell this that around points, this lemma tells you that around points with density small or density almost 1, you have a good decay estimate. And so this guarantees you that you have this density lower bound. Why we can't go on just another last thing and then I'll stop. Why can't we go on further in proving the regularity? Because we are not able to end with this situation. So what happens around the point with density exactly 1/2? So if I take a point that is in the reduced boundary, around the reduced boundary, you can have the boundary is almost flat. When you make a zoom around this point, you have the symmetric difference between some alpha space and the set E. This symmetric difference is small. And so can you prove that when this difference is small, then around that point the bulk energy decay in a good manner? And we do not prove this because we are not able to prove this fact. What happens if you take a ball and consider this simple problem? You have a P Laplacian with two different constants that is alpha on top for xn greater than 0 and beta down. Can we expect that this decay in a good manner? Because when you do the comparison here, you have not to compare with the minimizer of P Laplacian, because you have the alpha space. Here in the picture, you don't have the full ball all is complement. You have and you have to consider the half ball. So you have this problem when there are two different coefficients. So is it true that the minimizer, so this functional where there is these discontinuities between when you pass through the alpha space? Is it true that the gradient decay in this way? In that case, one can go further and try to prove also the other step on the road to prove the regularity. And that's all. Thank you for attention. That in Italian we say grazie.
Thank you, Luca. Thank you, Luca, for this wonderful talk. Now I request all the participants to put their questions in question and answer box, or they can raise their hand so that we can unmute your microphone and you can ask the question directly. Yeah, so in the meantime, Luca, on your result with Nicola Fusco in 2011,
Yeah.
can you comment something on the optimality of the epsilon that was there?
Okay, this result you mean? Yes?
Yes.
Sorry, I don't understand the question about. Can you repeat?
So the optimality of epsilon.
The optimal epsilon.
Yeah, so this half is.
Epsilon depends on alpha and beta. So the values of these epsilons depends on how close are these how close are alpha and beta, and so you can give you know that when these this ratio is equal to gamma n, you don't have any information. So this go to zero. But I'm not sure if it is optimal because it would be necessary to check the iteration lemma that you use to prove that. So I'm not sure that it is optimal. Okay. It's an interesting question. I'm not sure that it is optimal. Okay. But the bound I think is optimal when this ratio is greater than gamma n. Maybe the result is not true.
Okay. Okay. So I think we have received a question from Johannes Osborne. So he says, "Thank you for your talk. To what extent is it necessary to introduce the perimeter penalization in the cost functional?"
The perimeter penalization, in what extent?
Yeah, so maybe he can ask the question directly. Yeah.
Yes, hello. I was just wondering, because you mentioned early on in the talk that without you don't have well posedness from the very beginning, and so this idea of penalization with the parameter is what was introduced.
Yeah.
Yeah. And so I was just wondering, out of curiosity, to what extent do you think it's necessary to include this approach of this penalization in the functional?
I don't know. I know that if you don't have here this, for sure there are cases in which there are no solution. So so you have to add something here to guarantee the existence.
Yes.
And I don't know if you can think of adding something different, for example. I don't know if I answered to your question.
Yeah, that's basically it. If something else could be placed, but I was just curious.
Something else maybe could be possible, but the perimeter is very natural, as I said, because it considered the surface tension of, for example, if you think about this functional, here introduced by Murato and Novaga. Here, this from physical point of view, this term is exactly the surface the surface tension of the droplet.
Mm-hmm.
And you, from physical point of view, you have to consider that. So measure in some way this surface tension. Maybe it could be possible also consider something else, but it's natural to add here something that avoid you to spread inside the omega the set and to avoid the disintegration of it in very small pieces.
Mm-hmm. All right, thank you very much.
Thank you.
So, are there any more questions or comments?
Hello?
Yeah.
Yeah.
Hello?
Yeah. This reminds me, like, the relative isoperimetric problem.
Yes.
It's probably some variation of this, maybe for a particular case, maybe it may be just corresponding to the relative isoperimetric problem, right?
Yes. Yes.
Yeah.
Indeed, isoperimetric inequality is fundamental in the proof in some points. This is true because here at the end when you have this information, the density information, I write here. These give you also some information using the isoperimetric inequality on the measure of the set A. So there is an interaction between the measure of the boundary,
Yes.
the interface measure, and it is correct.
Yeah.
And indeed, also for the Muratov and Novaga functional, when, as I told you, the shape is exactly spherical.
Yes.
Then in that case, you have to prove in some way that the set that minimize this functional is exactly the set for which the isoperimetric inequality is indeed inequality. So it is a correct observation. Yes.
So I have one more, like, if you can answer this. So is it true even in this case that if your boundary of A intersects boundary of omega, then it will touch it orthogonally, something like that?
I don't know. I'm not. Maybe you have. It is possible. Maybe you have to also to add some regularity assumption on the set omega.
Okay. Yeah.
It would be possible. It's an interesting question. I didn't think about it, but it's possible to consider it. Yes,
Yeah.
yes.
Yeah. Thank you. Thank you for a very nice talk.
Thank you.
So, are there any more questions or comments? So, in case there are no more questions or comments, uh, let us thank Luca for this wonderful talk. Uh, and we meet again on next Tuesday for the last talk of this webinar series by Professor Sylvain Herberosa on control theory. So now I request all the participants to leave this platform. And I thank again Luca for this wonderful talk.
Thank you very much, and see you all.
Yes.
Thank you.